This video has been supported by PCBWay. Hey guys, we are dealing with broken ICs all the time. Occasionally they are just smokily snuffed out after being overloaded or connected in reverse. Other times failures are more interesting. Years of slow drift or a sudden malfunction without any obvious explanation. If only they weren't so damn small and hidden in tough black plastic packages to make matters worse. I bet we could learn a thing or two, not only about catastrophic failures, but also about the magical inner workings of semiconductors and how to pull their strings and make them work better for us. Maybe. All that is to say, I've been lusting after another microscope. And just recently a friend has helped track one down. I think he may have imported it from Japan and even organized some Japanese spare parts for it.
NANI?
Not an easy feat, I imagine. But he's working on one of these too, for multi-axis micromachining and Raman and laser-induced breakdown spectroscopy. Check him out, link below, if you want to see how deep this rabbit hole is, and leave a big thank you on my behalf. This is a Mitsutoyo FS70L, a decapitated head and Z-axis only. The L version being especially special, but let's postpone that to the very end. This is a metallurgical microscope, as opposed to a biological one, so it's made from metal, not meat. Oops, sorry, wrong script. It's made for viewing metals, not cells or bacteria. The biggest difference between the two branches in the microscopy technology tree is probably illumination. Biological specimens are suitable for through-sample illumination. IC packages kind of are too at a certain wavelength, but that's an advanced topic for another video maybe. Metallurgical microscopes use epi-illumination. Light is delivered coaxially through the objective, and reflections are viewed through the same. Thanks to my pusher's work, the microscope is fundamentally working already. There are only a few details left to address before we can proceed. I wouldn't mind having a stand for it, for starters. It would work horizontally too, but I would prefer not to if I can avoid it. I can just point a flashlight into the illumination orifice, but I'd rather make a dedicated fiber-coupled light source, so that I can have both hands free. Our brains have a kind of tolerance range, within which two slightly different images can merge together into the impression of a single image. There seems to be a small misalignment in the binocular eyepieces maybe, that prevents that from happening for me, so hopefully we can fix that. It needs some motorization for scanning larger areas in X and Y, and for focus stacking with the Z-axis. There is a very capable Basler C-mount camera plumbed in, with what seems like all the right accessories, but neither its focus nor field of view seem to be aligned perfectly with the binocular. So I can't film exactly the same thing that the eyepieces are showing me, unless I fix that. Last but not least, I'm getting kind of washed out low contrast images when feeding in higher intensity illumination. Not sure if that's just fringes and internal reflections caused by the numerical aperture mismatch of my flashlight and the fiber input. Whatever that is, it needs to be figured out. And then we can finally indulge in some semiconductor photography and reveal what the L is for. For the stand, I had planned to just glue some threaded inserts into an older granite surface plate, and then to erect a vertical mounting plate on there. For vibration elimination, some half-empty automotive air springs underneath the large mass of the plate would be more than sufficient for the application. That would be the budget option. Unfortunately, I have no budget left, after having spent all my Patreon money on this 400 kilogram vibration isolating optical breadboard. Yeah, it is tough being Marco Reps sometimes. But this decorative coffee table should also be a suitable microscope foundation. As a vertical mounting plate, I'm going to use what's called a Wandkonsole in Germany, or unistrut with wall flange everywhere else. Can you guess where I got that idea? This is strong but a crude construction material quality, with weld spatter everywhere. So to avoid pressing any imperfections into my coffee table surface, I'll smooth it over and deburr the edges especially. I've seen some decent results coming out of photogrammetry software lately. The conversion of a number of flat photos into a 3D model. So I thought I'd give that a try to ease further planning of the setup. Ooh, thank Torrent for the free trial of that software. Honestly, it's okay as a rough guideline. I'll 3D print an adapter plate to mount the microscope head to the struts. This deserves to be CNC machined later, but I want to iron out all unforeseen problems before committing to that. FS70 is a cool microscope, as I hope I'll be able to show you later. But what it isn't is popular, widespread and well known, so most things I'll have to figure out myself by hand. The manual is available, but it's superficial where it matters, and there's hardly anything published about it elsewhere. This part will have to withstand some squeeze in its Z-axis, so I printed it in ASA, with a few additional perimeters, 8 or so. I'm aiming for a gigantic working distance here. About half of that is going to be taken up by an XY motion stage. What's left afterwards is still going to be huge for high magnification microscopes. And that is kind of a key property of these Mitsutoyo objectives. They are made for the semiconductor industry, to work underneath, to position wafer probes, or to inspect and repair bond wires. This ×50 objective, for example, has a 17mm working distance, whereas comparable ones are practically touching their focal plane. I think I've overheard that the binocular and eyepieces were spare parts bought in Israel. Israel's eBay shops are a great source of specialty sciencey equipment and spare parts that are available nowhere else, but everything I've ever bought from there seemed to be absolutely smashed up and vandalized and dipped in salt water prior to shipping. So we can consider ourselves lucky this time, with only a bit of dust and a stripped screw or two. I suspect that these diagonal screws are intended for eyepiece alignment. Could be wrong though, I didn't find any documentation for this. But the fact that there is this suspected misalignment problem that is giving me double vision, and that somebody has evidently tried to get in here once, seems like a pretty good set of clues. Japan versus Japan, let's see who wins. It's I'm the one who wins for once. Well, depends. The binoculars are a bit more dirty than I would like, and mostly inaccessible for cleaning. But I found the big problem. That was some thread locker or another substance that seems to have escaped its hold and got on the crucial mating surface of the eyepiece socket, pretty much forcing that into a crooked position. Other small imperfections here don't matter that much. They are out of focus and contribute little to the overall image. Plus, this path caters only to imperfect human eyes. What I really care about is the camera output. And that is elsewhere entirely, but also dusty and in need of tweaking. This tiny little C-mount camera is a Basler ACA 2500, 20GC if you must know. Only 5 megapixel, but those are distributed on a large, sensitive 1-inch sensor. By plucking out its IR cut filter later, we could trade realistic color representation for a broader spectral response, which might be useful for some applications. The microscope optics project an intermediate image of a certain size on a certain semi-fixed plane. I guess they are pretty standardized, but choosing a fitting camera, based on not really published specifications, seems like an accomplishment in itself. Presently, the camera and eyepieces are matching nicely in terms of focus, but not in terms of field of view. They are close but pointing towards different centers. So I couldn't effortlessly do something while looking through the binocular and film exactly the same thing for YouTube with the camera. There's also some vignetting on one side, the dark corners, and a small mismatch in magnifications. Not sure if I can do something about those two. Nothing I've touched so far seemed to make a difference, and I don't want to touch too much without fully understanding it. If I could align foci and fields of view, I would be satisfied. It's a bit difficult though. Not only are the grub screws that are holding in the camera periscope in inconvenient locations, but there is also an unfortunate codependency between camera focus and field of view, and a third surprising parameter that would like to be taken into account when adjusting these things. This guy is basically just two mirrors. What I keep calling field of view, or maybe more accurately the center of what the camera is looking at, can be set very easily here, simply through how far we insert the thing into the scope body, and where exactly we point it. The aforementioned codependency of FOV and focus exists because insertion depth ever so slightly varies the length of this line. So if the image sensor is perfectly in focus in one position, it was before I had to fondle it. It will be no longer after a significant movement of the periscope. The clever creators of this microscope knew that, of course, and so they made the C-mount adapter slightly height adjustable. You don't see me cheering though and flipping to the next chapter. Unfortunately, the cam has its back right up against an adjustment limit already. If I point eyepieces and camera to the same center, and then focus based on the eyepieces, then I would need to bring the camera in closer to its final lens, or lower it into the adapter, to bring it into focus as well. But it is already as far as it goes. I could abuse this setting, the one for people with a mismatch in their eyes. This would elongate the eyepiece beam path, and bring it closer to one that would match the camera one. I am feeling pretty smug about my ocular perfection though, so I would prefer to keep these neutral on the white line for bragging purposes while it lasts. Or in case a wretched visually impaired person ever comes to visit and wants to use this. No, seriously, the camera path has to be shortened, or the eyepiece path has to be elongated for them to match. 3D printing a new low-profile C-mount mount that will really let the cam sink deep into its holder seemed like the least intrusive option for now. But this little power over Ethernet camera turns out to be quite power over Ethernet hungry, and it relies, guess what, on its C-mount threads for heat sinking. When sitting in a plastic ring, it can reach over 60 Celsius depending on the frame rate. Not lethal, but not optimal either, because I want low noise footage, and maybe even some infrared action later. So camera should be mounted with metal ideally. After spending a lot more time tweaking and researching and asking around, it is beginning to look like this might be mostly pointless. Yes, with minor modifications I can get very close to perfectly matching focus and field of view of eyepieces and one objective. This one being a ×50 M-plan NIR. Can you believe this working distance? Centering perfect, vignetting almost gone, confocality very, very close. But then on another objective it's different for some reason. This one being a ×10 M-plan apochromatic. Why would it be different? I don't get it yet. This is an infinity-corrected microscope system, meaning that the objectives are putting out what could be visualized as parallel light beams, which are then focused into various intermediate output images by lenses in the microscope body. If that's true though, how come different objectives can influence these upstream focal lengths? I'm counting on the experts to explain that one in the comments. So in short, I've done what I wanted. I've fulfilled my objective, but only for one objective. For the others, I guess we just have separate modes of operation. We will work either with the camera or the eyepieces. Or we'll have to find an autofocus camera, or another one of these ×1/2 reduction thingies, which was included with this affordable AliExpress camera. That can't stay here though, because the top TV port will soon be otherwise occupied. Let's try to get some motorization going. This is a manually actuated 3-axis wafer probe head. A Carl Zeiss Microtech PH150. Kinda Zeiss if you ask me. This beauty was donated by my friend Alex, who is YouTubing as Gears and Gear. As the name implies, he's covering test equipment, electronic artifacts, and now also CNC and lathe machining projects. And Soviet-era surface-to-air missiles? I think that deserves a few more subscribers. I'll leave a link below if I convinced you, and I'll try again in a minute if not. This actuator with pre-tensioned Schneeberger V-groove slides and spring-loaded backlash-free actuation claims to be able to point at 500 nanometer feature sizes on wafers, or 500 nanometer feature sizes on other things. It's wearing this kinky rubber skirt with which it can vacuum itself onto a probe station baseplate. And it's meant to use this arm with a needle clamped into the tip to get some reach and to bring the semiconductor parameter analyzer where it needs to be. My plan was to replace the arm with a little platform for my microscopy specimen. And that would have been nearly ideal, except for the problem of coupling motors onto these micrometer screws. Their knurled bits move in and out, and so we would need to do something flexible. Rubber O-rings as drive belts or something like that. But not sure how well these will withstand permanent radial loads in operation. So I think it might be better to use a proper, purpose-built microscopy XY stage for this job. Such as this one, for example, a Merzhäuser-Wetzlar EK14 auto stage. This one has stepper motors attached already with rack and pinion. Translation ratio feels pretty coarse, so we will have to microstep these as much as possible. I don't need hundreds of nanometer resolution. My best objectives don't even have that much resolving power. But this is now a sports thing, of course, so we'll see how fine I can go. The yellow knobs on the motor shafts are inertial dampers. Not sure if those still make sense with extreme, maxed out microstepping. The rack in the rack and pinion drive seems to be somewhat compliant to eliminate backlash. Even though this is an OEM accessory for clamping onto this round Olympus-style flange, and even though I certainly didn't buy it from them, the manufacturer has kindly given me the D-sub connector pinout. So we can go right ahead to our sponsor PCBWay and get our motor driver prepared. I'm actually just going to recycle what I made for my nanovolt scanner multiplexer rotary switch thingy. Absolutely nothing special, just many stepper drivers connected to a Pi Pico. PCBWay is not only a great partner to Marco Reps and many other YouTubers, but to the open source community as a whole. They are a platinum level sponsor to the KiCad project, which everybody benefits from. Their affordable, fast and unbureaucratic rapid prototyping services enable research and development on any scale, and not just in the electronics field either. Have a look at the PCBWay Community Projects Hub to find inspiring projects based on their 3D printing, CNC machining, or laser sheet metal fabrication services, and then give them a try yourself. Today we're only using the good old reliable bread and butter 4-layer circuit board. It's a simple one with way too many axes. I only need 3 today, maybe 4 later, if I also want to hack into the motorized objective turret. One small difference between nanovolt scanner and micro motion control: the latter can tolerate Wi-Fi traffic right next to it, and that would actually be quite convenient, not running an extra USB cable all the way there. To use the Raspberry Pi Pico W's onboard antenna for this efficiently, a keep-out zone on the motherboard is recommended. I violated that here because that wasn't planned, but if I just mount the board at a distance on pin headers, it should be fine, I think. Normally I'm happy to sacrifice some convenience to program microcontrollers in nice and clean and predictably performant C code. Not today, I think. This doesn't need performance, just a happy little web server, where I can either click buttons myself or have another program control a larger focus stacking or panorama stitching operation. So I think I'll just use MicroPython this time and just gobble up all the external convenience libraries. Not exactly my style normally, but to be honest, it's quite impressive what one can pull off with that. This whole thing is cobbled together from stuff I had lying around. And so the XY stage motor and home switch connections take a little detour over an HDMI cable, which happens to have the correct number of pins. I will publish all of these 3D models, of course, for everybody else who wants to mount their FS70 on Unistruts and an Olympus XY stage on a metric grid breadboard. Only completely normal and sane combinations happening here today. Our Z-axis has this lovely, smooth, gearbox-reduced fine adjustment knob, perfect for a gentle friction grip attachment of another stepper motor. My first version was shaped around the knob and gripping it more tightly, but because of never quite perfect coaxial alignment, that had a tendency to deform something and ever so slightly shift the microscope image around. That's why now I went for a more compliant grip with that rubber seal string. And yeah, this works. Not entirely sure yet if HTTP GETs are the best interface for letting another software take control of this, but it'll do for now. It looks like stepper motor angles, gear ratios, and 1/16 microstepping work out to about 8 or 9 micrometers per microstep. If we just go in one direction, we can use that resolution. But if we turn around, there seem to be a few micrometers of backlash under some conditions. No persistent losses though, so at least my first MicroPython thing is able to count up and down, so there's that. This recording already has pretty good illumination, so let me show you where that is coming from. This is not a trivial point in my mind. Like, I'm here with hardly any prior microscope experience, and so I'm not sure how much light we need, or how important the spectrum is. Do we need a high CRI LED? Are there any benefits to RGB illumination maybe? Are there ever? As a starting point, let's consider this original Mitsutoyo branded halogen light source. This is a generic outsourced product available from many brands. It's usually called FOI-1 or FOI-150, fiber optic illuminator. But the questionable internals are usually made by a US company called Techniquip. I'm calling it dubious because this one has been fished out of the scrap, where it has landed probably because it blows up new 20 euro bulbs instantly. Even if it didn't, the 150 watt projector bulbs for this thing have a 50-hour lifespan normally. But knowing this part, we can memorize a very high 840 lumen number, and the excellent CRI number that is usually associated with halogen and incandescent lamps. Furthermore, I find it dubious that it uses a not isolated autotransformer, with European mains going into a 230 volt tap, and a 115 volt tap being left open unused, while the 115 volt cooling fan is fed through a huge scorching hot power resistor dropper. It has partially burned the PCB underneath. A third 22 volt circuit gets regulated by a nice EMI emitting thyristor dimmer circuit, so that must have gotten stuck wide open for new bulbs to detonate immediately. What I like most about this thing is the sleek black enclosure with the logo on the front. So that is all I'm keeping. I'll replace the murderous auto transformer with a reasonable little Meanwell 5 volt switcher. And for the actual light source, I thought I had a good selection of high quality, high power LEDs from a few years ago. Well, midlife crisis trigger warning, turns out they are from over 10 years ago. And power LED technology has made a few quantum leaps since. So just looking at the lumen numbers, these would not be very good. Mike's Electric Stuff on YouTube has recently shown something that AliExpress calls laser LED beads. They don't laze, but I think these will be very suitable for several reasons. They have a decent lumen per watt efficiency, a small emitter spot size and a flat front. So I hope I can press one right up against my fiber bundle entry face for a very low loss coupling. The original halogen bulb has a kind of parabolic reflector to help funnel light into a fiber as well. But seeing how most of the enclosure inside walls have suffered from photo bleaching, I suspect we may end up with similar usable lumens. I'll cut a little heat spreader out of copper sheet metal, and that will be stuck to some leftover internal aluminium frame parts with a thermal interface adhesive. Intuition and Discord server agree. Sending 5 watt through this is pushing it a little bit, But if I see excessive LED temperatures, I can just cut another piece and double up the copper. The constant current driver is just a super conventional voltage reference into potentiometer, into op-amp, into emitter-follower power transistor. No PWM interference in my microscope footage ever. I also swapped the heavy metallic mains-powered cooling fan for a lightweight low-power plastic one, which I expect will cause a lot lower vibrations in the vibration-sensitive vicinity of my microscope. And here's the aforementioned low-loss coupling by way of smooshing the fiber right up against the diode. And that's pretty much where I'm at right now. Yes, wavelength or spectrum matters, because a microscope's resolving power depends on wavelength and numeric aperture, but short of going monochromatic, there's not much I can do about that. Yes, more optics for a kind of maximally defocused Köhler illumination to smooth over a possibly uneven LED spatial output, or any pattern coming from the fiber bundle would be good, but I'm pretty sure that that is already built into the microscope head, so not much more to do there. But one more thing to do in general. When using higher intensity illumination like this, without having closed down the aperture diaphragm as far as it'll go, I'm always seeing a huge loss in contrast, especially at high magnifications. A completely unattractive, washed out image. And I suggest I'll save us all some time by not going over all the things I looked at, only to find them innocent in this matter. Turns out the problem is a huge internal reflection mooning us on this side wall, and leaking back into the image uncontrollably. I'm told that normally FS70s have some anti-reflective lens flocking type material there for exactly this purpose. Not entirely sure why it's missing here, but it could be related to the FS70L version, and that posing a fire hazard if you know what I mean. If that turns out to be a real concern, I might have to look into a more heat-resistant beam dump or light trap attachment. But maybe not made from a glossy thermoplastic in that case. For the time being, I just ordered a small sample of this Wile E. Coyote Acme portable hole material. The old goth in me would like to point out that he's not rejoicing at this. But I suspect that's only because we didn't buy enough for a hoodie. It's pretty impressive. I'm not even sure if the camera can do it justice. A small piece of that, sticky taped to the sidewall, solves our last bullet point. And we are ready at last for some semiconductor photography. Well, almost. Semiconductors don't just grow on trees normally. They tend to be pretty well hidden, and nowadays it's even harder to extract them. I wish all the others would surrender their contents as easily as this one, having been nicked by a Dremel diamond disc, and then just peeled open. I assume this used to be some kind of DSP, preceding some output amplifier hybrids, in a Wandel und Goltermann antenna analyzer. Oh, it had Wandel und Goltermann internal markings on the package? But the chip itself is made by LSI Logic Limited in the USA. In an indeterminate year around 1998 it seems. I think they went out of business or got absorbed by some conglomerate. I can't read silicon yet, obviously. I'm just here to look at pretty pictures. And pretty they are, aren't they? The dye looked grey to the naked eye, but on closer inspection it reveals all of those vibrant colors, depending on layers and process steps. They are calling this an analog digital compacted array, so I think my DSP guess was not that far off. I would in fact double down and guess further that this repetitive, high-density area is some form of programmable gate array where application-specific, high-speed, high-efficiency math can be implemented. And this coarser stuff at the bottom could be some analog functions, DACs, ADCs, analog switches, that sort of thing. Ooh, there's more delicacies where that came from, some FPGAs. That'd be short for flat programmable gate arrays in this case. These Altera Flex parts really earn their name. As far as I can tell, they are a die bonded to a sheet metal heat spreader. And then the BGA fanout? Do we call this fanout too? Is realized with a fine multi-layer flex PCB. There's still the typical epoxy resin encapsulation over most of the die, and I don't have a way of stripping that indoors, so this will have to wait. Yeah, decapping epoxy molded packages is going to be the main challenge here. There are a few different strategies, none of them easy or fail-safe, but for victims where I could effortlessly get more, where it doesn't matter if I break a die, I prefer the Curious Mark's friend method, because it's quick and needs no spicy chemistry. The idea is to overheat a part, making it a bit rubbery. 400 degrees Celsius hot air works well for me. The molding compound is usually infused with sand or something, to make it flame retardant and to better match the temperature coefficient of thermal expansion of silicon. That makes the package a bit brittle, and through strategic twisting motions, if we've reached appropriate softness, the package can be broken in half without breaking the die. The lead frame, if any, will usually just pop right out. But typically the die will still have some adhesion to the remnants of the package. I couldn't help but notice that very specifically modern analog devices parts seem to have vastly improved adhesion of the top of the die to the molding compound. I don't believe they care that much about decapping. It's probably just a side effect of their formulation. But yeah, those are difficult. With other brands and older parts, one can reheat the leftovers and lever a clean die out of the wreckage. Or if there's no angle of attack, this stripped down fragment could be escalated to another strategy, which boils down to boiling down in acid. That might not be an option for many, and not for much longer, if we allow ignorant politicians to continue restricting reagents, simply because they could be abused for something. If that is seen as a valid reason, there won't be much left soon. This is 68% nitric acid, which does something at high temperatures. But at effective temperatures, it's evaporating pretty quickly. If we only have one part, one try, one die, there is no way to break it in this method. Some experts can even get parts to functionally survive this procedure, expose the die but leave bond wires and pins attached. At 150 Celsius in a loosely lidded beaker, it can take hours to dissolve most of an epoxy package. For proper, clean and efficient decapping, you want red fuming nitric acid, but I can't legally have that in the European Union, of course. That doesn't mean that it couldn't be created based on one of many YouTube videos on the matter. I wouldn't know. Let's continue. A third option without restricted chemicals, so far, could be a slow cooking in colophony rosin. Exactly the old-timer soldering flux. Smells absolutely delicious and nostalgic, but probably shouldn't be indulged in too frequently. And maybe we also shouldn't maintain a molten puddle of it on a circuit board for hours, because some slow interaction with polymer links makes this an attractive decapping method. It's not fast, and not risk-free from what I hear. I'm told that when doing this over a flame, the stuff can be ignited, and that will end in a lovely, sticky, sooty snowfall that's hell to clean up. Same as before though, for die preservation this is a low-risk operation. After a few more hours, the victims can take another bath in brake cleaner or similar, and we can already see the first few flakes of molding compound coming off. I tried this on 2 chopper-stabilized op-amps. It worked nicely on the 80s vintage ICL 7650, of which I have swapped many in a Solartron 7081 multimeter. It led to an unusual result in a modern analog devices ADA 4523. Here the die, except for the bond pads, still seems to be coated in something brown and shiny. Could this be the reason for all the new interesting ADI parts being such a pain in the ass to decap? I suspect this could be an elastic PDMS silicone, with which tempos of thermal expansion of die and molding can be decoupled, thereby improving thermal performance and reverse engineering resilience. I made a Python script that sends X, Y, and Z movement commands to the Raspberry Pi Pico-based stepper motor controller. In X and Y, it traverses an area of interest to take pictures of everything with 30% overlap. At each stop, it advances the Z focus axis a little bit too high. Then it takes a series of test images while lowering the z-axis through the expected previous height and ultimately ending a bit too low. The test shots gathered here are scrutinized by OpenCV, and their sharpness is evaluated and assigned a focus score, based on a function called Laplacian. This is all on GitHub, of course. The highest focus score image is saved, the height returned to, and that becomes the center around which the next shot's autofocus is searched. Oh, the things I do to avoid leveling out my setup precisely. The resulting gigabytes of images are then stitched together. Adobe Photoshop, the expensive option, has a specialized tool for that, but it just asks, "Give files," before launching an all-night-long processing orgy. It ultimately culminated in this. I'm sure one can make it work somehow, but it seems kinda inefficient. That you can't feed it the position and overlap information, which would make the processing much easier. So I'm using Fiji, a pimped version of ImageJ, which is open source, and loaded to the gills with powerful scientific image processing features. Its default built-in stitching plugin works for me, but an even more potent version seems to be available via the Update and Plugin Manager. This one will accept my helpful metadata input, and therefore the processing won't take exorbitantly long. Well, it could, I'm sure, if you shove some gigapixels into it. Without further ado, here's the 1980s ICL7650 chopper-stabilized operational amplifier, all stitched and ready to enjoy. My video editing software crashed while trying to handle the full 800 megabyte file, so this is slightly downsized, but you get the idea. If anybody knows a good no-bullshit file hoster to serve the whole thing to the masses, please leave a comment. I'll upload what I have, if only to make room on my local drives. Yeah, so isn't it amazing how they pulled off such a complicated part? Using a number of semiconductor elements that you could conceivably count on only 4 layers or so. Well, here's the exact opposite of that situation. This is a modern auto-zero operational amplifier, 2 equal channels. This is the ADA4523 from earlier, after a bit more cleaning. Love to see some lore about one of my favorite parts. Apparently this was destined to be named LTC 2069 originally. It kinda raises the opposite question, what on earth do they need all of this stuff for? It's just an offset removing op-amp, not a supercomputer. I sure hope they don't secretly mine Bitcoin in my precision analog electronics, or report energy consumption of my voltage standards to the government. It's so complex, and not even just on the surface, it goes many layers deep. I don't even. My YouTuber friend Gears and Gear, who is still waiting for your subscription, has also sent over some semiconducting delicacies, such as this lid that was mere seconds ago still protecting a lovely high-G incorporation of an ADXL193 single-axis MEMS accelerometer. Such MEMS or microelectromechanical devices are semiconductors with moving parts. They have little gaps or bridges etched into the die to form things like tuning fork oscillators, or even a high-resolution array of little articulating mirrors for projectors. This guy just has this large, central, elastically suspended frame that can move a bit as a reaction to acceleration, which would then be picked up by a capacitive sensing method. That sounds pretty hard to believe in my opinion. I bet they are just making that up to secretly mine Bitcoin or to spy on us in our electronics. So let's try to use this part's self-test feature, which is a voltage input that can drive a forcing cell to electrostatically displace the moving frame. Nope, looks like they covered their asses pretty nicely here. The die is too photosensitive. As soon as there's enough light to image it, everything becomes railed and non-functional, including, I assume, the self-test feature. Even with weak infrared illumination and under UV anyway. Oh look, it's another supercomputer. This is AD71772, the 2-channel 32-bit Sigma Delta ADC that's at the heart of the open-source hardware CERN digitizer that we built a while ago. This is the largest image I've ever handled, 1.36 gigabyte for the whole thing. And I finally figured out how to apply some kind of flat field correction to each frame, so this should be much more uniform. The device doesn't consist of 2 large symmetric channels. It's just one ADC, its accessories, and 4 analog switch selectable inputs. Maybe these are the input switches? Because there's 4 of them? No clue. Large parts of the die are unfortunately hidden under metal layers. But in between we do still get a good look at the subsurface Factorio structures. These have to be precision resistors. I know precision resistors when I see them. Is this memory or Mordor? That's a lot of memory if so. Maybe some correction factor lookup table for the ADC. The one ring is also on the way though. Now I feel like we've got a bit of an unfair ADI overexposure. Texas Instruments have been absolutely on fire lately in the precision analog department. And in the spiffy bathroom tile department. This colorful piece of art is their JFE 2140, an ultra low noise matched JFET pair. Associated, it seems, with former Burr Brown research, this one seems to be marketed primarily towards the audio field. But accidentally or not, its excellent low frequency, low noise performance also makes it suitable for electrometrology. There is an excellent nanovoltmeter project on GitHub using a couple of these. It looks like my decapping process has etched away the wire bonding pads, giving us an especially intimate look underneath. And here is some of the very fabric of reality hanging out on the side. Bit of a sloppy job with the dicing saw. If you aren't careful in these uncertain areas, you might catch a glimpse of the microscopic eldritch horrors that lurk there, hodling their bitcoins. Since we were talking about old and new chopper op-amps a moment ago, here's another specimen worth considering. This is Texas Instruments OPA 2192. Modern Auto-Zero parts are pretty well behaved generally, but their periodic switching and rerouting mechanism that they use to get rid of their VOS inevitably causes some input bias current ripple, which can make them unsuitable for working behind high impedance sources. CMOS parts like this one have a deliciously low and steady I bias, and with TI's E-trim technology they can now be trimmed to very impressive levels after packaging. In many cases these are sufficiently good to replace choppers. I was kinda hoping to see the actual polysilicon E-trim fuses on here. But no, I don't think so. It's not only this very effective metallic speckle pattern. It's also a really complicated die underneath, so I probably wouldn't find anything. But yeah, TI E-trim op-amps, very good parts to be aware of. Okay, one more ADI part, so to speak, and then we do something else. This is a $900 integrated circuit. A multi-axis MEMS precision inertial measurement unit. Factory calibrated everything, wide temperature range, and it survives 2000 times gravity. I'm not yet in the missile building business myself, and to prevent such dual-use technology from falling into the hands of that one warmongering country that my viewers like the least, I'll try to dissect it and air out its secrets. It has excellent specs overall, but I believe the 2000G survivability is responsible for most of the price tag. Such G-forces will turn a 2-gram part into a 4-kilogram pull, so that'll require special construction techniques, if not overall potting. No? Actually doesn't look potted to me. Awesome. There's actually only $100 worth of components in here. There are 2 ADXRS 295 ultra-low noise gyroscopes, the 290 version of which costs $20, and an ADXL 355 3-axis accelerometer, mounted vertically on a daughter board, $60, and a little flip chip ADUC microcontroller, which costs them more or less nothing, I assume. It reads the 3 sensors, does some math, and makes its conclusions available via SPI. Yeah, the daughter board was attached nicely. That'll survive some Gs, but not sure about continuous vibrations. ADXL 355, hermetically sealed package, contains a stack of dies actually, the lowest one likely being readout electronics and interfacing. And on top of that there's a kind of sarcophagus for the MEMS part, likely filled with a controlled gas. All the silicon coated in silicone. The lid can just be chiseled or pried open with a scalpel blade. If I had some hot air here, I might have taken it in one go. The pharaoh's grave does not contain any valuable treasure, unfortunately. Only the second most abundant element on Earth. The damage is already done here, and I have this inner voice demanding that I poke this fragile MEMS frame to see how elastic it really is. Not an honorable deed. I don't even have a clean, not curled over needle. On the other hand, surrender, where are you hiding the bitcoins? Well, okay, as you wish. Hard to believe, but the ADXRS 295 gyroscopes are even prettier. And luckily for them, my malevolent inner voice is satisfied for now. I believe these discs are excited to rotate back and forth around their central hubs, ever so slightly at their resonance frequency. But then what's actually measured and processed downstairs is their pitch and roll due to Coriolis force, so tilting motions out of the resting plane. I lied about the inner voice, by the way. It's still there. Shout out to FlashForge for having made one of the most affordable, fully enclosed, snappy Core XY 3D printers. Its speed and precision helped this project every step along the way, and installing a community-developed Clipper firmware on it made it a real pleasure to use. So anyway, much more stuff to do. I've hardly used my x80 objective so far. The focal plane of that is thinner than silicon layers typically, so it's a bit hard to use and probably needs focus stacking to produce something enjoyable. But I've got to stop for now, lest I ruin all my fancy parts for pretty pictures. And anyway, the most interesting modern dies all seem to be locked down and hidden away under unnecessary metal layers. Why does anybody even bother? For somebody who can clone your chip, it'll be trivial to remove some layers. Me personally, I seem to be stuck with peeking through gaps in the upper layers. Or am I? What if I could make my own gaps in nearly all materials, custom shapes, and pretty much all depths? This is the specialty of Mitsutoyo FS70L. Its internal optics can not only deliver friendly white light illumination, but also some very angry photons. For this purpose there is this exclusive OR shutter mechanism that blocks either the eyepieces or the top TV port. The Galvo scanners and f-theta lenses in typical desktop fiber laser marking machines are ideal for rapid scanning over large areas. What they are not super good at is focusing a beam into its absolutely minimal spot size, and drawing stuff with geometric perfection. It can only approximate with its natural tendency to draw things round. An aerodynamic, intrusive proboscis like this might be a challenge to draw for a Galvo scanner. That's why focusing through a microscope objective and positioning with a Cartesian XY table are preferable in precision applications. When I made my last video about one of these desktop marking machines, I did not yet know about the open source community's accomplishments in figuring out the language to talk to the JCZ controller cards in these. Thanks to a project called Balor, we now have a complete API for these, making them even more powerful. Imagine automatic exploration of those tedious color engraving parameters, just to name one example. Yeah, I'm just going to point that roughly into the hole. I could imagine a much nicer semi-permanent setup, but I can't live without my laser for very long. My software just leaves the Galvo mirrors in their central position, pointing straight down, and then it demands a short impulse of the absolute lowest power possible. This is dangerous after all. I could fry some dirt on internal optics and damage them. I could send a beam severely off-center and ablate some wall or mounting ring, releasing dust in an objective. Or I could develop a taste for lasering huge craters into Uranus. Or other celestial objects. I didn't forget to substitute my new velvety wall with some Kapton tape for this first test run. There doesn't seem to be a lot of stray IR hitting that, so that can probably go back. But yeah, seems to work fundamentally. The machine's cooling fan impersonates a kind of air assist. Hopefully that will keep my objective clean until I get something better. The refraction limited minimal spot size I can accomplish here is unfortunately not 1064 nano, but about 3 micrometer, due to a dependency on numeric aperture. For comparison, the affordable f-theta lens that came with the laser engraver gave me about 13 micrometer minimal spot size diameters, and that was very good already. Let's try to wrap this up for today with one practical application. This is another one of my favorites decapped, an NOMC 1603 thin film resistor array. 1 kiloohm per element, with fantastic TCR tracking across the board. What if we wanted a slightly different ratio? I'm not seriously suggesting that we get a useful part out of this, but just seeing the discoloration and the residue around the manufacturer's laser trimming marks, maybe it is less problematic than I thought. Let's say we are using a combination of these resistive elements in a voltage buffer with some gain. Our output happens to arrive at 9.97 volt or something, not 10.00, so we just need the slightest adjustment. Conveniently, every resistor has a narrow and a wide section. Taking a byte out of a narrow section is a coarse adjustment, a large increase in resistance. Carving a little bit out of the wide section is a fine adjustment. That's what I'm aiming for here. It's not clean or controlled or anything, and there's probably metallic residue with less than optimal TCR. But a fine adjustment has been made, and we can refine that another day. I hope I've shown you something interesting today. Thank you for watching. Should we try to point a pulsed UV laser in there next time?